What do you get when you cross a turtle with a porcupine?
I don't think I want to find out.
Porcupine?
You have to tell us.
A
A
portal?
slowpoke. A slowpoke.
Nice.
Ooh, you figured it out. I was just going for weird words.
Was that
Am I
it?
going to be vindicated? Am I going to be vindicated?
Come on, Warbash. Did he get it?
Is it slowpoke?
Because that's good.
I'm always excited, David, for Fairweather, especially when I can guess a joke.
So as mentioning, the hey, Warbash is slowpoke, very good. I was talking about this beforehand. Elon Musk linked to an article in his Twitter feed written by Universe Today that was syndicated on another website that wasn't Universe Today. And so we didn't get a mountain of traffic on the website. Instead, this Universe Psi, some other website. Anyway. So every now and then, the downside of like, go ahead, use my content, put it anywhere you want, feel free, backfires. But Elon Musk, Papa Elon, liked a comment that I made. So it was a very good week. Let's say hi to a bunch of people.
Hello, people.
Hello to Aaron C., Astro B., Avi Scott and Flower, Bob Harkins, Capital H, Daniel McCool, David Dunn, David Fairweather, Douglas Crandall, Eric Charland, Grant Lanning, John Musk, John Victor, Johnny J., Jorn Albert, Larry Beckham, Mr. Tom Harbin, Nancy Graziano, Nightbot, here to help us out and protect us, Paranor, Rick Schwartz, Ryan Spagenberg, Scott Bragdon, Susie Murph, Tom Van Scotter, Warbash, Jonas Ofri, and Zap Van. Hey, everybody. So, before we get started, I think it was Capital H. You have to tell me if this was you, Capital H. He or she noted in the comments of one of my question shows that, you know how you can use the sun as a gravitational lens if you go to a 1,000 astronomical units, that there must be binary stars out there where the two stars orbit each other at about 1,000 astronomical units. And I double-checked. This is a thing. That have natural gravitational lenses. So just like we have a natural, the moon happens to be the same size as the sun in the sky, you would have these binary star systems where they could look across and they could just watch Einstein rings from behind their that other star.
So this is a thing, not with binary stars, but this is the entire field of microlensing, where you wait for chance alignments between, you look at some distant object and you just wait for like one of those distant objects to flare in brightness in a very characteristic way. And you know that something has passed between us and acted as a gravitational lens, which amplified its brightness. And this is a planet hunting method. It is a black hole hunting method. It is a stuff hunting method. Proud to say, pioneered at the Ohio State University.
Nice.
In the 1990s. The technique was first ridiculed because who could possibly design stuff to do that? Turns out the Ohio State University can. And now that is exactly how WFIRST is going to find planets.
Yeah.
It's also the only way that you can find free-floating planets.
That's right, the rogues.
Yeah.
The rogue
and potentially
planets.
even moons have been found.
Do you see rogues in infrared if you're good enough?
Not likely against the background. They'd be extremely cool by that point.
So I just thought it was a great idea that, if you were lucky enough to be in some binary system, you could have another star that's just this natural telescope that's allowing you to peer out into the universe all the time. Be cool.
That would be really cool.
Yeah.
To like sit on the surface of a planet and just see Einstein rings.
Yeah, around that other star.
People gather for a nice sunset.
Right.
Instead, you gather for a nice Einstein ring.
Yeah, exactly. All right. Well, let's move on to the show. 1 second here.
Oh, I should start recording.
Yes. Hey, good call. I was going to forget to record as well. And now I didn't.
Well done.
Let me get my rundown.
You're welcome.
Anyway, so that is absolutely going to be in a question show that I'm going to do because I think it's such a great idea. All right. Hello and welcome to the Weekly Space Hangout for Wednesday, June 27th, 2018. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about an update for James Webb Space Telescope. Good news and bad news.
Don't hold your breath.
Well,
I wonder what it is.
missing baryons found at last. Venus is changing day. Oumuamua is a comet. Organic molecules bubbling up from Enceladus. And if we have time, the fastest computer in the world can make pretend universes. We're all living in a simulation now. Joining me.
No.
Let's just wait. Let's just wait till we get to the show. You wait, Mr. Paul Sutter.
Hey, it's me, the cantankerous one in the corner.
Oh, it's all right. There's a lot of stuff that you like. Just the topics
like
just the topics that we want to bring up are the ones that you have the problem with. Yeah. True. And also,
cheese.
And that other voice
and cheese again
is Kimberly Cartier. Kimberly.
Hey, Fraser, happy podcast day, everyone. I'm the optimistic one in the other corner.
No. I think the optimists.
Zen.
I think we optimists now outnumber the pessimist. If Morgan's not here, unless Morgan is the pessimist. Anyway, speaking of Morgan is traveling, so he wasn't here last week. He's not there this week. Sadly, he won't be able to join us for this final episode of the Weekly Space Hangout for this season.
No.
Yeah, stressed out there.
Yeah. So we are going to be taking a couple of months off. This is our last show. We won't be here for July and August, and then we'll be back in September. So, sorry. Now, that doesn't mean that people aren't going to be doing things. Kimberly, you're still going to be writing. Paul, you're still going to be doing a million other things.
Stuff, here and there, seeing people.
Yeah.
I've got some friends,
Yeah.
Wait, what? You have other friends besides us here on the Weekly Space Hangout?
Kimberly, that cuts deep, all right?
And I always say this, but now I'm really, really serious. You should join the Weekly Space Hangout crew. This is why this Weekly Space Hangout crew was created in the first place, which was to provide everybody a place to go and hang out and keep each other entertained and their minds sharp and talk about space news over the course of the summer so that when we return, everyone is still a family. So go to wshcrew.space and they will they'll set you up and they'll provide you with a group of friends to keep you busy over the summertime until we can all get back together again the fall. So, all right. And no guest. It's just us. So hit us with your questions as they pop into your brain, because we'll need to stretch a bit, maybe.
Or even before, we want it unfiltered.
All right, let's get on with the stories. All right, Kimberly, hit us with the news.
All right, so today at NASA, there was a press briefing with some higher-ups in NASA and the James Webb Space Telescope giving us an update on what the status is of the telescope, when it's going to launch, and how much it's going to cost. And obviously, it's going to launch tomorrow, and it's totally on budget.
Nice.
Actually, it's under budget, totally. Mm-hmm.
Yeah.
Sigh of relief.
So the
Except
good
that
news,
didn't happen at all.
Right, but the good news is it's going to launch. It hasn't been canceled.
Maybe?
You keep saying that. You guys keep saying that.
I'm sorry. That's not what they said at all. In fact, they said many of the opposite things to what I jokingly said. If you recall back in April, NASA called for an independent review board to look into why James Webb has continually been delayed. They've been studying the system over the past few months. They finally released their report to NASA and to the public, essentially saying that further delays are inevitable because of lots and lots of mistakes. They said it more politically than that. And the earliest we could expect James Webb to launch now is no earlier than March 30th of 2021, which is
it's about 10 months after the last
3 years from
estimate.
It's gonna be bald and old man by then.
Yeah.
Oh wait.
Yeah.
No, I'm sorry. And in order to accommodate this additional delay, the total cost for the telescope is bumped up to $9.7 billion, which is an extra $800 million above what the last estimate was. And reading through this report, there are 32 different recommendations from this independent review board to NASA on how to fix the problems that they
so
discovered.
what's the
And
problems? Like, who's screwing up? What's getting
so
screwed up? Why
so
don't
so what I understand, and I listened to part of this press briefing, which included some people from Northrop Grumman, who are the ones building the spacecraft and the sun shield of James Webb, while the NASA scientists are building the instrumentation. It seems that most of the issues are on Northrop Grumman's side, building the spacecraft and the sun shield. The report lists as the issues human error as a huge issue, embedded problems, so things that were flawed from the beginning and then got built into the design and then they find do not work, lack of experience, excessive optimism about the schedule was listed, and the complexity of the instrumentation and what they're trying to do, and some of the human errors that they detailed in this independent review were things that I feel like any experienced engineer should know not to do. Things like
don't spill coffee on the
or don't spray solvent on a valve without first checking if that valve and that solvent are compatible.
Right.
And that required replacing a lot of valves in the system. There was wiring that was not tested before the power was turned on for an instrument. Essentially, it was wired. The manager accepted the word of whoever wired it and didn't do any further tests before putting power through the system and overloaded the system, one of the systems. In one case, they unfolded the sun shield and a bunch of bolts came off and scattered everywhere, including some that went into the spacecraft that they haven't found yet.
They'll float
These are
free
some
in
of
orbit.
the instances that...
And how much money has been spent already?
Already there has been more than $8 billion spent.
And there was a line in the sand,
but
right?
they estimated that these human errors are costing about $1 million a day until they are fixed.
Yeah.
So these are the issues.
What's going on here?
All right. So we're in
how bad this is being
done.
So
So it seems to me that NASA, when they decided to partner with Northrop Grumman to do these, either there was some communication issues, there was organization issues, or some promises were made that the company could do this and build this, and are not living up to what they promised. Because it seems that the NASA instruments, they, according to this report, are still on target. They're passing all their tests, all the spectrographs and things that are going to be mounted on the spacecraft itself. Those are going fine, according to the report. Right. It's really the contractors' bits that are having issues. And so whether there was overconfidence or promising more than they could deliver, or there was not enough oversight during the process, or not enough independent checks along the way.
I still can't wrap my head around this. Like, this isn't the first rodeo. This isn't the first time that NASA has worked with contractors to build a complex, expensive spacecraft observatory.
And the first time that Northrop Grumman has built a spaceship.
Correct.
So
that I think that they're sweeping that under the rug of the instrument is the most complex thing that anyone has ever attempted to build, and there are unforeseen things, and no one could have anticipated how complicated it could have been, even though that's the whole point.
Yeah, well,
anticipating of all these designs and planning is to anticipate how complicated it's going to be.
And anybody who has ever worked on any kind of project, like a software project or an engineering project, knows that they go wrong all the time, and the budget creeps, and like, this is par for the course. This is absolutely standard.
This is a really big budget creep.
Yeah.
Since it was accepted back in 1996?
It's up from, a couple of $1 billion to close to $10 billion by the time it's all done.
What about the follow-up missions? Because like W1 can't fly until James Webb flies. Whatever comes after W1 can't fly until W1 flies. And so is the entire slate of NASA's space-based missions pushed back by 3 years?
Well, it's worse than that.
It's possible.
They've all NASA at the same time, or just like about a month ago, they released another report to all of the project investigators, the principal investigators for the main missions that are going to be part of the decadal survey, and they said, you'd better sharpen your pencils. You're going to have to bring your budgets down. When before they had been told to design things like LUVOIR and HabEx and such with much larger budgets, they're having to bring these numbers down at this point.
They have to keep accommodating these increases in budget. They're going to have to go back to Congress this year, next year, and 2020 in order to continue funding James Webb. And like you said, you can't launch W first until you launch Webb. And if there's no budget and the scientists are tied up in doing that and the engineers and the contractors are tied up in doing that, it's a cascading problem. And on top of that, one of the reporters was asking about the Ariane 5 rockets because Webb has to launch in one. And they are getting phased out. They may be gone. And at this point, you can't redesign Webb to launch in a different rocket. So the administrator sort of sidestepped that issue. Didn't really go into a lot of detail about how that would be affected, but I imagine there'll be additional complications having to preserve one of these rockets just for Webb, keeping it running and maintained, and additional costs because of that.
Well, maybe they could put they could take an old Ariane 5 rocket fairing, they could put the James Webb inside of that, and then they could put the whole thing inside a BFR and then launch it that way.
Or we could just build 20 Hubbles,
connect them all up into a big interferometer,
a super Hubble.
Yeah.
So James Webb,
this sucks.
I mean that's the only word to say it. It sucks.
The saving grace is it hasn't been canceled.
It's too big to fail.
Yeah.
It's too big to fail. It has not been canceled.
Everyone keeps saying that. At some point, I legitimately worry that people are going to get fed up with it and scavenge it for parts.
Yeah.
Right.
Like, it's something I don't say very often because I try and be very optimistic about Webb because otherwise I will cry. But at some point, I worry that people will get fed up with this whole process. And like you say, well, what during this time we could have been building XYZ, 20 more telescopes and doing this science.
Right.
And it's an argument we've had on the show before is where do you put the effort into big stuff or little stuff or both? And how do you judge that? At some point, I feel like we may be hitting the tipping point.
Yes.
Yeah.
Where it's no longer worth the effort that you've put in.
Yeah. I think this speaks to something bigger happening in the physics and astronomy community, that if we believe that the only way to advance knowledge is with giant facilities, whether something like the James Webb or the LHC or a big supercomputer, and these kinds of projects become ever more complex, ever more Byzantine, ever more risky to actually build and design with decent amounts of time and money. In the meantime, that's hurting our ability to do science with our proposed science with those missions. So where is that trade-off? Why do we keep pushing in this direction? Is it time for some introspection of the precious amount of money that we're able to get from society so they can keep doing this science thing? Are we really getting the best bang for the buck?
Well, that'll be the next generation's problem because James Webb's going forward. It's happening.
Still.
Yeah. What about some kind of space-based interferometer network? Crack the interferometry problem and then just launch additional Hubble telescopes, as you said.
Visible interferometry is very, very tricky.
But in space, it
has nothing to do with the atmosphere. Space doesn't solve problems. Space creates problems.
Well, but I want my terrestrial planet finder is what I'm saying. That was the plan. And they were going to build they were going to build an interferometry mission, CERT, and then SIM, that's what it's called, Space Interferometry Mission. And that was going to be a test bed for space-based interferometry, and then they were going to turn it into the terrestrial planet finder, and that all got canceled. But, you launch a telescope and bring new telescopes into your constellation one at a time. Once you crack the interferometry problem. All right, well, this sucks. Paul, bring it around.
All right, for some happy, exciting news. You know those missing baryons we've been looking for? It is not just composed of socks. It is a different kind of, or it is the same kind of material. It's hydrogen, it's helium. It's been found. So yeah, we can check that one off the list and move on with our lives. Yep, we're done. We're done. Science is over.
All those cosmologists can become planetary scientists now?
Oh, a bad taste in my mouth.
Okay.
All right. All right.
Ignore me, Paul.
So
keep talking.
Now, a great way to sort of describe this, right, is that these are the missing protons and neutrons in the universe, not the dark matter, not the dark energy, the regular matter that was also missing, which it's kind of amazing how little of the universe we really knew.
Basically none
was there. Is there.
We know how much protons and neutrons and electrons there is in the universe. We have data from the very, very early universe that sets very, very hard limits of how much quote unquote normal matter there is. Then we have observations from a few billion years into the history of the universe, into the Big Bang, where we see that amount of matter. And then we go around to the present day universe, and our census is about 30 to 40% short of the counts we were getting from the early universe. So obviously it had to go somewhere. And the conclusion is this normal matter didn't disappear. It didn't evaporate. It just went to places where it's hard to see it.
And so what?
So where is it?
Yeah. So it's been found. Where is it? What is it?
It's long been, so it's obviously not in galaxies because we checked. It's obviously not in clusters because we've checked. And so the only place left in the universe that's not in a galaxy, not in a cluster, is in between the galaxies, in between the clusters, in the loose filamentary structures of the cosmic web itself, where these are relatively low density environments, not vacuum, but just a little bit above vacuum, spread out over huge volumes. And this combination means it's very, very hard to detect stuff in there because it's not very bright and it's spread out over a large area, so it doesn't give off a lot of light. And there have been some hints of detections of hydrogen and helium in these filaments. This most recent announcement is a Nature paper led by Nick Castro out in Rome. Instead of looking for the hydrogen, the helium, looked for other elements that give better signatures. And in this case, they looked for doubly ionized oxygen. And they looked at quasar light filtering through billions of light years of this very thin material. And they found signatures of oxygen in this filamentary structure. And if you do some rough guesstimates of how much filamentary structure there is, and if you see this much oxygen, then there must be this much hydrogen and helium, presto changeo, you get the missing baryons.
And what could generate that much oxygen? Because oxygen is something that comes after the formation of the Big Bang. And for it to take up that much of the universe, it's kind of a surprising material to be seen streaming out into the universe.
Oh, for sure. And that's a big question is, okay, if hydrogen, helium, and even more exotic things like oxygen are out there basically in the voids between galaxies, how did they get there? How did they get so hot? When did this happen? There's a lot of questions surrounding that. Now we've just replaced, this is the usual progression of science. We've answered one question or potentially answered one question. Now we have a dozen more.
That sounds about right for science, though.
Yeah. No, that's job security. This is very basic stuff.
Thunderduck is noting, asking, enough oxygen and hydrogen to power a spacecraft? Sort of an interesting idea, right? That, we know there's lots of hydrogen out there, but maybe there's a lot of oxygen out there too that you could then harvest up and,
It's
turn
pretty
into
far
a
away
rocket.
stuff, though.
Yeah, it's still, the density of this
this
stuff is still incredibly small.
This would register as a vacuum on the Earth.
Right.
It's basically none, but they happen to look through a very, very large volume, so they're able to pull out this very weak signal. And it is a pretty weak signal. I'm looking at the plots right now.
But it's significant enough to claim missing baryons.
Yeah, but it's a Nature paper, and the saying is, it's a Nature paper, it's probably wrong.
Oh,
So
Poor Nature.
it's poor Nature.
I didn't know that was the thing.
This is
It is the saying.
This is where you put your really, really exciting stuff, because you want to make a big impact, and then the exciting stuff usually turns out to be wrong.
Right.
No wrong.
Yeah. I mean, I think the Bicep 2 announcement of primordial gravitational waves was found in Nature. I know what you mean, though.
I wouldn't be surprised.
Yeah, that a lot of those big, exciting announcements, it's the biggest, most reputable journal. And so you're kind of swinging for the fences when you post something in that. And hopefully the data holds up. But science is kind of hard on you.
And I want to point out to the chat, I'm not just bitter because Nature has rejected many of my papers. I'm not bitter.
Nope.
I'm nothing against the fine editors and referees of that publication. It's just saying that I'm passing along.
It's that you haven't tried hard enough. You haven't really thought out of the box yet. You're still in your...
And that's why I don't have a Nature paper?
Yeah, because you're in your cosmic box. If you, something that's going to change everything, that's going to be the one that you're going to need to send along.
And it will be wrong. Oh, and don't get me wrong. Most of my papers are also wrong. They just happen to not be published in Nature.
Right.
Science.
Oh, all right. Let's move on. So I'm going to go next, and let's start with Oumuamua. So,
Yeah, what's up with Oumuamua?
Oh, so we all remember Oumuamua, right? This was this interstellar asteroid that was found sort of October-ish, 2017, and it had this really interesting trajectory as astronomers were jumping on board and finding, sort of tracking its movement through the solar system. And it turns out that the trajectory was not an elliptical trajectory that was within the solar system. It was actually on a hyperbolic trajectory that took it into and then out of the solar system again. And this was sort of the first time that an asteroid had been seen doing this. And as astronomers got on board, and every telescope in the world sort of turned to face the this asteroid and track its positions over time, and they were able to tell that it had this really strange kind of tumbling that was going on. And based on that sort of change in brightness, they got this very strange, almost cigar shape to it. I'll bring up a picture here for the folks that are watching.
The artist rendition.
Yeah, the artist rendition. So, some astronomers from the European Southern Observatory have published a bunch more data on this, and it turns out that the motion of Oumuamua was different, and let me see if I can get the picture up here, was different from what they were expecting. So essentially, if Oumuamua was a sort of solid rocky asteroid, or maybe even metal, to have this kind of really strange cigar shape, then it should have had a very predictable path through the solar system, because it's very heavy and really hard to, for the sun's solar wind to be able to push it around. And what they found instead was that, in fact, it was a little bit off of the predicted position, exactly as if it was a comet that was outgassing. So the new guess is that Oumuamua, it was not an interstellar asteroid, but it was an interstellar comet. And
so this outgassing is shoving it a little bit and fro, changing the tumbling or the path just enough to make it not asteroid-like.
Yeah, and so the movement of it matches what you would expect from a comet, not an asteroid. And this is not the first, interstellar comet that's been seen. Others have been seen in the past. So, speaking of things that were wrong.
Is this? I mean, because Oumuamua is different in almost every way than stuff we see in the solar system, right? It tumbles on a weird axis. It has this ridiculous elongation.
It has
It
this
has
weird color too.
lovely, lovely rouge. And so, maybe it is it really like conclusively, yes, this is a comet based on some analysis of
No.
soil gassing?
No, and so here's the part that's kind of weird, right? Which was that they did a bunch of observations and they never saw a coma, they never saw a tail, they never saw any of the features that you would traditionally expect with a comet. It was very asteroid-like in its structure, and so the theory is that maybe it vents with they called it unusually large coarse dust grains. So it could be that it's venting in a way that is different from the way the traditional comets do here in the solar system. And it's still definitely interstellar in origin. So there's enough really interesting stuff about this object now, I guess we have to call it, that it warrants all kinds of
It has
further
a name. It
study.
has a name. Just
Oumuamua,
call it
yeah.
Oumuamua.
But the
First of its name.
yeah, and so this is the problem, right? Comets. I mean, they have these vents on them, and they act like a thruster, and so the comet, as it tumbles, is sort of shifting itself in funny directions, and this did that too. So
This is a hypothetical question for the group here. When we first saw hot Jupiters, we thought, wow, that's really crazy. And then we realized that hot Jupiters are really common. And it made us rethink of what the standard, quote unquote, standard structure of a solar system ought to be. And the standard solar system doesn't really look like our kind of solar system. Could this be a case where we have a standard picture of comets and asteroids and their relationship and their dichotomy? Could it be that this is the harbinger of our picture of what is an asteroid, what is a comet? Could be totally off base.
Maybe.
Well,
I
Kimberly,
mean, we do.
we've seen comets around other star systems, right?
Yeah, we've seen comets around other star systems plenty of times where there's chaotic transits and comas and tails from disintegrating objects going around stars. We see this a lot, but Paul, I think that it could very well likely be that this may be something different than what we see in our solar system. It may end up being that asteroids and comets may fall more along a continuum of tiny uh, primordial objects that date back to the start of the solar system. I mean, here in our solar system, we sort of have asteroids in the inner part, we have comets in the outer parts, and they don't mix. They don't seem to mix too often, with barring the occasional comets that sweep through. But maybe other solar systems are different. Maybe they mix more. Maybe the materials mix more. I mean, certainly we see some asteroids in our solar system that have localized deposits of material that, if heated up, could outgas like a comet. There's some surface ices and things like that may act like a comet if given the chance. So this could be something totally different than what we see. Or it could just simply be we didn't get good enough measurements while it was passing through very unexpectedly. It's certainly not coming back, so we can't get more measurements, um, which I would like. I think one of the things that would be really interesting is if we could find an asteroid in our solar system and do sort of a thought experiment of what would happen if we took this and chucked it out towards another star and see what sort of material science would happen. Like, take material science and say, what would the surface of this object do if we flung it around like a comet? Would we see something like a Oumuamua? I don't know.
There you go.
Anyway, maybe not an asteroid, maybe not a comet, but maybe something.
So, I mean, again,
A muoid.
Oumuamua, yeah, a whole
Are we
new
going to
class
name a
of
whole
object.
class of objects around it now?
Yeah, let's make
An
it happen.
Oumuoid? That's a lot of vowels.
I like it.
Usually consonants win in a word, and it's time for the vowels to have their shot. Like
Where's the Y going to fall?
in the middle.
So I'm gonna my co-hosts have no idea that I'm doing this, but I'm going to do a quick picture. If you guys want to go and look at the Planetary Society blog written by Emily Lochtawal today. Last week we talked about Rygu and how Hayabusa 2 is now reached Rygu, and we had a really kind of cool animation of it last week, and now it's even closer. And Emily Lochtawala from the Planetary Society put together a picture where she compares Itokawa and Ryugu. So Itokawa was where the first Hayabusa went to in 2005, and Ryugu in 2018. You can see
And
sort
I've
of the
been
difference.
saying Ryugu this whole
Ryugu,
time.
right?
I have been saying Ryugu.
Ryugu's fine. I don't know. I'm just making it up. So
I thought you.
I'm
no.
sure that there's an actual pronunciation
Yeah.
somewhere.
Yeah,
I don't think
I'm
that
sure
we
they're
know
on
it.
their way to my email right now.
Please tell us.
So,
Or
but,
chat, help
so it's
us.
bigger. It's bigger. It's a lot bigger. So
Okay.
Itokawa was half a kilometer by 0.3 kilometer by 0.2 kilometers, and Ryugu, is that what you're saying?
I'm saying
Is a kilometer,
Ryugu.
and it looks like an 8-sided die. It looks like you could play some D&D with it.
Looks like you
looks like a
the
diamond.
small and medium options.
Yeah.
But like Itokawa looks sort of like a kidney bean,
Yeah.
almost.
It's
A comma.
they all look like this kind of conglomerate pile of debris.
Bunch of junk, if you ask me. Yeah.
Yeah, it looks like just like
Hey,
a ton of
don't call
concrete
them
or something.
asteroids junk.
They're not junk. They're just junky looking.
Yeah, there's a difference. They're
They have a
precious.
heart of
They
gold,
have
though.
They're
have
precious
a-
treasures that look like space garbage.
Precious science treasures.
Precious science treasures that just happen to look like space garbage.
No, it's like seriously, pick up 2 different asteroids, 10 different asteroids, you'll get 10 different shapes.
It's
pretty
got
awesome.
13 different shapes.
Yeah, because 2 of them will turn out to be binary,
See, told you.
like Ultima Thule.
Right. Oh man, can't wait for that.
Ooh.
All right.
That's the villain in the new Marvel movie, right?
Yeah.
Yeah.
Kimberly, let's talk
Well,
about.
I'm to stuff with my pop culture.
Paul,
Totally
we're
up
going
to
to talk
date.
about the changing day on Venus, right?
That's me.
That's you. Oh, right.
That's me. We are gonna, but Paul is welcome to comment.
Don't worry about it. No, Kimberly. Now I see how everything's all mixed up.
I
Go ahead.
generally talk about planet stuff.
Yeah.
I like planets.
Especially when Morgan's not here. All right.
It's true. So the question is, how long is a day on Venus? And you'd think that answer would be standard in, your Astronomy 101 textbook, but it turns out that it actually depends on when you measure it. So here's what happened: is that back in 1990, Magellan went to visit Venus. It measured the day of Venus and found it was approximately 117 Earth days, because Venus, though it orbits counterclockwise around the sun, it actually rotates clockwise. It's a weird planet. And then flash forward to 2006, and the Venus Express measured the day on Venus, and its measurement differed from the Magellan measurement by about 7 minutes. And it was a real difference and not an instrumental difference. They checked that very thoroughly. And so the question is, what's going on? Why are there 2 different days on Venus? And the answer...
Good question.
So the answer actually comes from Akatsuki, which is the Japanese mission to Venus. And when it was observing the upper atmosphere near an area called Aphrodite Terra, it noticed a very strange, prominent ridge in the atmosphere. Think like a stream flowing down a river, or flowing down the stream bed, hitting a rock, and just a bunch of water piling up against the face of the rock and just stopping there. That sort of thing, but with atmospheres. And it's a type of phenomenon called a gravity wave, not a gravitational wave, in the atmosphere. And it was just sort of stationary, this giant ridge in the atmosphere. And they were wondering what it was, why it was, and if that could possibly explain some of the difference in Venus's day. So what they did is they used existing models of Venus's atmosphere to try and figure out what sort of phenomenon could cause this sort of bunching up of Venus's thick atmosphere. They found that it is totally possible just based on the daily temperature variation, the 117-day daily temperature variation in the atmosphere that causes some components of the atmosphere to rise when it gets hot and sort of separate out and bunch up against the top of a plateau. And that's exactly what's happening. And because Venus's atmosphere is so thick, this is a very large phenomenon, and it actually causes torque on the planet that slightly nudges the rotation rate. It totally does.
I was going to ask if this is affecting the actual rotation on the surface, or our ability to measure it. And you're telling me that the winds are like Superman and they're like stopping the rotation of the planet.
Not quite
and
stopping,
setting it back in time.
But this giant, when you combine this giant ridge with effects of angular momentum exchange with the sun, then yes, it can cause a up to 7-minute difference in our measurement of the rotation rate of the planet. So it turns out if you measure it during the afternoon, Venus's afternoon, then you get a longer day than if you had measured it at midnight. How crazy!
That's awesome.
I mean, these gravity waves happen all the time. We have them here on Earth, but on Earth they're so much more subtle. And because our atmosphere is actually relatively thin compared to the size of our planet, they don't really cause much noticeable effect. I mean, you can measure them, but they don't really do much.
What's the temperature difference we're talking about here?
Oh gosh, I don't know that number, but between the day and night of Venus, it gets
no difference.
Pretty big difference.
No.
Like, no.
The day, or
am I thinking of Mercury?
Yeah, no. In the
I'm
actual, within the atmosphere of Venus, it doesn't matter where you go. It's always 460 Celsius.
I was thinking of Mercury.
Poles, night side, day side.
Then I guess it can't be that big of a temperature difference.
Yeah.
But it causes enough. It causes enough of the atmosphere to sort of rise when it gets warm during the afternoon to actually bunch up and cause this giant gravity wave.
Very cool.
So it's Venus's day.
It's hilarious that they're still trying to work out. They only just have a sense of how long a day on Saturn is. So.
Well, I think that also depends on where you go, and when.
Because it's like you want to define day as the surface, but do you mean what layer of the atmosphere, where in the atmosphere, the solid surface? Is there even a solid surface? Does that even matter? Who cares? Because we care about stuff that we see with our eyeballs.
So like with Venus, the planet itself does a complete rotation in about 117-ish days, but the atmosphere itself goes all the way around the planet in about 4 days. I mean, how do you define it? Sunrise to sunrise, but where and when? Apparently, when you start measuring actually matters.
And the sun in the sky, because Venus rotates backwards, but it takes so long to do it. The sun goes in the wrong way. You could walk faster than the sun is moving.
I mean, I wouldn't want to walk on the surface of Venus. No, but I'll take your word for it.
If you could outwalk the sun moving. You could outwalk the rotation of the planet, and it's in the wrong direction anyway.
Yeah,
it's all messed up. All right.
So Venus has lots more issues just besides the runaway greenhouse effect. A lot more issues than that.
Raise your hand if you find Venus more interesting than Mars.
Me.
I do.
Yeah.
I want to go back to Venus.
That's whole panel 100% unanimous.
100%.
This was one of the things that's really kind of frustrating me. There's no spacecraft at Venus now, and a million spacecraft at Mars. Like, we need another rover at Mars. Okay, fine. I want the Mars 2020. Okay, the Mars 2020 be all right, and the helicopter, all right, maybe, and the sample return mission would be pretty cool.
And InSight.
And InSight would be pretty great to know if there's...
And Marco?
Yes, please. Okay. But the point is that we don't have anything in the works for Venus.
Hey, can we take all that money we're wasting on the web and saturate our solar system?
What do I want more? Web or to understand Venus?
Web.
Can we point Webb at Venus?
No, we can't.
Yeah, we can.
We pointed Kepler at the Earth and it almost drowned out the CCDs.
They're planning to
probably
use
shouldn't point
Kepler,
Webb at Venus.
Or they're planning to use Webb for observing the Great Red Spot on Jupiter.
Yeah, they are.
They just announced that.
Don't we have Juno like right there?
It's
So here's the
infrared.
question. Will Webb launch before the Great Red Spot dissipates?
That
It is slowly shrinking.
That was exactly what I put in my tweet when I mentioned this. Is like, while there's still time.
Oh, I didn't know. Sorry, I'm not plagiarizing.
No. But it's the obvious joke is that James Webb is taking so long to launch. The Great Red Spot might have disappeared by the time it does.
Venus will still be there.
Mercury might get ejected from the solar system.
By the time James Webb's got to hurry.
Yeah,
shake it off, James Webb, but not like.
But not the bolts on the sun shield again, please.
Yeah, in the washers.
Keep those there.
All right, let's move on. Paul, you want to talk about a fast computer that can make pretend universes?
Yeah. Do you like computers?
Yes.
No.
Oh. Do you like giant computers?
Yes.
No, that's even more terrifying.
Yeah. Would you like a computer with over 200,000 cores?
That's a lot of cores.
I could watch a lot of movies.
You could watch a lot of Netflix. It is. So the supercomputing facility at Oak Ridge National Laboratory has just unveiled their greatest supercomputer yet, called Summit. It is I don't think it's quite official yet, but it is going to be the world's fastest computer, capable of 122.3 petaflops, or 122,300 trillion calculations per second. That is a lot of.
That's a big number.
A lot of, yeah. And these kinds of computers are general purpose scientific platforms. They're like an observatory where they have a certain design characteristics, certain capabilities, and then people propose like, okay, I want to use this observatory to look at this thing for this amount of time. And another group will say, oh, I want to use this set of capabilities. I want to look at this thing for this amount of time. I want to do this kind of survey. This is a general purpose instrument where scientists propose, oh, I want to run some kind of simulation using some fraction of the machine or the whole machine for a certain amount of time and get some science result. And a lot of the most extensive simulations of our universe itself are done on giant machines like this. So there are baby universes being born, evolved, and killed, usually because of a mistake, inside of computers like Summit. And I just wanted to point out that there's this entire area of scientific research that takes place in silico.
And that's it's a pretty important thing to do, because a lot of the theories that they come up with to be able to sort of like, how did the universe work at the largest scales? What were the first moments after the Big Bang? How did you get from the galaxies coming together before to the universe that we see around us today? And that is done, a lot of it is just done by coming up with a model and then simulating it to ever greater levels of detail, and hoping that the universe that you see in the model, in the simulation, looks kind of close to the one that we have today.
This is exactly it. So you can't solve these problems, these math problems, these math equations with pencil and paper. You can only iterate them, evolve them to see how they play out. And then you're right, you add more and more details, the more and more powerful computer you have, the higher resolution, the greater chunk of the universe, the more complicated physics operating at different scales you can toss in to your simulation, bake a universe, and compare it to observations.
So aside from universes, plural, are there other astronomy problems that this computer could help solve?
Yes. So one of the biggest things that's done on supercomputers like this is studying supernova, the final moments of a star's death and the first couple seconds of the ignition of a supernova, both core collapse and type 1A, are exceedingly complicated kinds of problems requiring a lot of hot and heavy physics operating in very complicated non-trivial ways at very, very short time scales, but over vast distance scales. And the only way to really probe the interior through theory of understanding how a supernova goes off is with a computer.
Well, that's really awesome.
It is awesome. There's also problems in galaxy formation and star formation. Basically, any complicated problem you can think of, both in astronomy and other areas of science, is done on a computer.
Yep.
Well, I have to say, I never did anything quite so complicated as to need a supercomputer, but if I did, this seems like the dream that you would want to apply for.
It's a dream and also a nightmare, because usually these kinds of cutting edge machines are really, really finicky and difficult to deal with. And there isn't a lot of embedded knowledge in the community of how to use them. So it's like a tool that can solve all your problems if you can only figure out how to use it. And so sometimes researchers tend to use older systems or less powerful systems because they've been around longer and they've been tested better. They're more reliable. So there's a balance here. But if you need 200,000 cores to solve your problem, there aren't a lot of options.
Right. Or if you want to simulate reality and then make the people there wonder if they're living in a simulation.
Yeah, and then there's a seg fault and the whole thing crashes.
Oh, blue screen of death. All right, so I've got one last story here before we wrap things up, and this is, now you all remember when they found hydrogen gas seeping out of Enceladus, which is one of Venus's moon. Sorry, no, Saturn's moons.
Saturn.
And this was super exciting because it means that a lot of the ingredients for life are there on this ice moon of Saturn. You've got water that's below the surface of the ice that is making its way up to the surface through cracks and venting off into space. And then I guess about a year and a half ago, they found this hydrogen gas, which is food for bacteria here on Earth. And they found that also leaking out into space. And so now they've made another analysis of some of these geysers, these ice geysers that are coming out of Enceladus. And what they found was even more interesting, simple organic molecules. So they've got, let's see. So Cassini flew through and it used its cosmic dust analyzer and ion and neutral mass spectrometer to make measurements. And then they looked at this data and they found large, complex, carbon-rich organic molecules. So,
yes.
So even more sort of, building blocks for life, food for life, it's all there on Enceladus. So at this point, we're ready to go. We're ready to find life on Enceladus. All we've got to do is send another mission back to land, dig down beneath the ice, and swim with the Enceladasian space whales.
Cousins of the
European space whales, yeah.
All the organics are everywhere, man.
Yeah. Well, and they also found them on the
everywhere.
surface of, more of them than expected on the surface of Ceres, and they find them just in deep space.
They're here, they're on Mars, they're on Ceres, they're on Titan, they're on Enceladus now.
Yep.
They're progressing. Actually, it's not too surprising. They're on Titan. We've seen them rain from the rings onto Saturn's atmosphere. They're on Enceladus too. That whole planet moon system is just seeded with organics all over the place, and water and interesting moons all over the place. I was just saying this last week. These ingredients are everywhere in various combinations. At some point, they have to get it right again. Yeah. We can't be the only one where the ingredients were in just the right ratio at just the right time.
The only ones in the observable universe. Sorry.
No, Paul.
There's been a final paper has been written about that.
No, Paul.
More debate is necessary.
That's it.
No, Paul.
Which makes you wonder, where are they all? All right.
They're underneath Enceladus' ice,
right.
Swimming around.
Swimming with the European space whales.
Missing baryons.
They're the missing baryons.
In
All right.
Intercluster space.
So instead of a shameless self-promotion this week, I would love to know what your plans are for the summer. What are some interesting projects you're going to be doing over the summer that people should be keeping an eye on? Kimberly.
Ooh, I'm just going to be trying to frantically keep up with all the amazing science news that happens over the summer. A lot of scientists, especially geoscientists, take their research trips during the summer when they don't have to teach. So a lot of amazing science comes out during these months, as well as, well, I just moved into a new house, so there's lots of projects around here, but probably won't be able to keep up with that too closely.
That'll keep you busy.
But sometime in the next couple months, perhaps, unfortunately, the Kepler mission will breathe its last breath in outer space, which will be a very sad time. But I will be writing about all of the fantastic things that it has done to revolutionize exoplanets, as well as our understanding of life, the universe, and everything.
Paul, what do you got planned?
Let me see. Next month, I will be filming season 7 of How the Universe Works for the Science Channel. We've got some really great metaphors coming your way. And lots of hand gestures, and then cuts to CGI, and then back to hand gestures. It's going to be great. So I'm filming with them in July. That season will be out probably early next year. And I'm also warming up some very cool art and science projects. I'm working with a modern dance company based out of Manhattan called Siren Modern Dance. We're doing a project talking about time, and that project launches this July. We're doing a big party in New York, and then we're going to collaborate. And I think our first performance is scheduled for sometime in December. I'm also working with a local artist here, a local playwright on a very cool project. So I think my summer is getting lots of cool projects started.
Like as if you don't need enough cool projects.
I like the cool projects.
I know.
They are cool.
You're the hardest working man in space business. Space
What
show
about you,
business?
Fraser? What are you up to?
In less than a week, I'm flying to Australia for the first time
What for?
For the Star Stuff convention, which is going to be July 7th and 8th in Byron Bay, Australia. So I will be giving a talk there, which is going to be a lot of fun. And I've never been to Australia, so I'm really looking forward to that.
It's a pretty cool country.
I have to.
Oh yeah.
I have to work on my presentation some more. But I'm going to be talking about the golden age of astronomy. So talking about, James Webb and all these new cool telescopes that are coming, and ground-based and space-based and techniques and all that. So that's the big thing. I've got my hands on and have learned to use this really great automated telescope, robotic telescope from Oceanside Photo and Telescope. And it's an amazing machine, and I'm still like, it's kind of like a race car, and I'm figuring out how to do this. So the plan when I get back from Australia, is to crank it up, and we'll start doing some live astronomy observing with a bunch of our friends. So I think you all remember when we used to do that, so we're gonna do that again. So those are the big projects that I'm working on. Plus, we've got lots of more episodes that we're shooting, and other new projects that we're working on. So it's going to be, again, a fun summer of work. Even though we'll be on hiatus, we're all going to be working our tails off. So all right, well, and again, one final reminder to everybody, which is that you should take this opportunity, if you haven't already, and go to the Weekly Space Hangout crew. This is the group of fans who organized the first time we did a hiatus, and they've been hanging out ever since. So go to wshcrew.space, and they will welcome you with understanding, loving arms, and they will help set you up and help you find a bunch of other space peeps to yak with over the summer and share the news while we're all working on other projects. And we will be back in September. All right, let's put this on the gallery view. There's everybody.
We can Photoshop Morgan in.
Oh, poor Morgan.
We'll get a cardboard cutout.
Just like,
put a camera on it.
There's Morgan.
Webcam on.
All right. Thanks, everybody. As always, thanks for watching us live. Thanks for everyone who's listening as a podcast. Couldn't do this without you, and we look forward to seeing everybody next season. See you later.
Bye.